Ah, yes. The start of the common era in human civilization. Much of the world is firmly in the grip of Augustus and the Roman Empire. To them, academic matters are not of interest. Only politics, military might, and infrastructure development under the banner of Roman culture are. But in the Far East, a whole different paradigm has been culminating for centuries. The civilizations of China and India are of far greater antiquity than those of Greece and Rome. Dating of mathematical documents from this time, however, is no easy task. For example, Zhou Suan-ching, generally considered to be the oldest of mathematical classics from China, has estimates for its age differing by almost 1,000 years. Unfortunately, like every nation does at some point, ancient China experienced academic turmoil in 213 BC, when the Chinese emperor ordered the burning of books. I will not mention their name, so as not to give recognition, even if it is infamy. Anyone that orders the unjustifiable killing of people or the systematic destruction of knowledge should never receive any recognition or attention of any kind, even as an antagonist. They should exist in unending seclusion from all social order. So we must begin with the work that we can not only reliably date from ancient China, but also that survived the counterproductive book burning. And that work would be, perhaps the most influential of Chinese mathematical insights, the 9 chapters on mathematical art. While compiled over many centuries, we have evidence suggesting the latest stage of the work occurred in the 1st century, with meaningful commentary coming from Liu Wei in the 3rd century. Maybe the most significant portion of this book is Chapter 8 for its solution of problems in the system of linear equations using both positive and negative quantities. The last chapter involves 4 equations and 5 unknowns, which is the most in the text. We, however, will look at problem 8, which is 3 equations and 3 unknowns. The problem has been translated as follows.
Now sell 2 cows and 5 sheep to buy 13 pigs, surplus 1,000 cash. Sell 3 cows and 3 pigs to buy 9 sheep. There is exactly enough cash. Sell 6 sheep and 8 pigs, then buy 5 cows. There is 600 coins deficit. Tell, what is the price of a cow, a sheep, and a pig, respectively?
During this time, the Chinese relied on arrangements of physical counting rods made of bamboo, ivory, or bone, ranging from 3 to 14 centimeters in length, and a board to solve the problems on. This gave rise to a written numeral system called rod numerals that uniquely included different colors, such as red for positive and black for negative, the complete opposite of what we use today. In our modern syncopated system, the problem presents as follows. The solution is found to be C equals 1200, S equals 500, and P equals 300. As we can see, the Chinese repeated the old custom of the Babylonians and Egyptians by compiling sets of specific problems with general solutions. Contrast this with the more insightful composition that deduced propositions from an initial set of axioms like that of the Greeks. Several centuries later, mathematical progress in China would again rear its head from the pile of ash. The Chinese fascination with the value of pi reached its high point in the work of Tsu Ch'ung-chih. In fact, he would find the familiar Archimedean value of 22/7 and describe it as inexact, further articulating what he deemed an accurate value of 355 divided by 113. More specifically, he gave 3.1415927 as an excess value and 3.1415926 as a deficit value. this remarkably good approximation was not equaled anywhere until the 15th century. The calculations by which he arrived at these bounds were apparently aided by his son Tsu Ch'ung-chih and were probably contained in one of his books, since lost. Once again, though, we should bear in mind that accuracy in the value of pi is more a matter of computational stamina than of theoretical insight. During this era, there were mathematicians working in various parts of China, but relations between them seem to have been remote. We evidently have relatively few of the books that once were available. It is not until around the 14th century does another remarkable mathematician arise from China. So in the meantime, we travel to ancient India and the archaeological excavation sites of Mohenjo Daro, where evidence of an old and highly cultured civilization existed during the time of Egyptian pyramid builders. Even more so than in the case of China, there is a striking lack of continuity of tradition in the mathematics of India. Significant contributions are episodic events separated by intervals without achievement. Shulva Sutra's work containing geometry, completed in about 100 AD, was plagued by orthodox Hindu tradition that boasts of astronomical work more than 2 million years ago and calculations that lead to billions of days from the beginning of Brahman. In the early days, myths infiltrated the works to present an astonishingly inaccurate production of results. Surya Siddhanta follows Shulva Sutras around the 4th century and 5th centuries AD, but there are obvious similarities between portions of the Surya Siddhanta and the trigonometry and astronomy of Ptolemy several centuries earlier. Even if the Hindus did acquire their knowledge of trigonometry from Alexandria, the materials in their hands took on a significantly new form. Thus was born, apparently in India, the predecessor of the modern trigonometric functions, known as the sine of an angle. And the introduction of the sine function represents the chief contribution of Surya Siddhanta to the history of mathematics.
There is no doubt that it was through the Hindus and not the Greeks our word sine, through misadventure in translation, has descended from the Hindu name Shiva.
It is now the year 476 AD, traditionally marked by the fall of the Western Roman Empire, but also recognized as the unsung birthday of Aryabhata, author of a major work titled Aryabhatiya, dated to 499 AD. Even more so than in the case of China, there is a striking lack of continuity of tradition in the mathematics of India. Names of several Hindu mathematicians before this time are known, but nothing of their work has been preserved beyond a few fragments. There were even 2 mathematicians named Aryabhata, and we cannot with certainty ascribe results to the elder one. The Aryabhatiya is somewhat akin to that of the Elements of Euclid in Greece, both summaries of earlier developments compiled by a single author. Where they differ, though, is the Elements is a well-ordered synthesis of pure mathematics with a high degree of abstraction, a clear logical structure, and a clear pedagogical inclination. The Aryabhatiya is a brief descriptive work in 123 metrical stanzas, intended to supplement rules of calculation with no feeling of logic or deductive methodology. The work opens with names of the powers of 10 up to the 10th place, and then proceeds to give instructions for square and cube roots of integers. Rules of mensuration follow, and about half of which are erroneous. The area of a triangle is correctly given as half the product of the base and altitude, but the volume of a pyramid is also taken to be half the product of the base and altitude. Again, in calculation of areas of quadrilaterals, correct and incorrect rules appear side by side. Although medieval Hindu forms of the 10 numerals differ considerably from today, the principles of the system were established there. The new numeration, which we generally call the Hindu system, is merely a new combination of three basic principles, all of ancient origin: a decimal base, a positional notation, and a ciphered form for each of the 10 numerals. Not one of these three was due originally to the Hindus, but is due to them that the three were first linked to form the modern system of numeration around 600 AD. It is worth mentioning that the Hindu symbol for 0, which is also ours, a goose egg. Although the Greeks had a concept of nothingness, they never interpreted this as a number, as did the Hindus. In fact, Brahmagupta comments,
Positive divided by positive, or negative by negative, is affirmative. Cipher divided by cipher is not. Positive divided by negative is negative. Negative divided by affirmative is negative. Positive or negative divided by cipher is a fraction with that for the denominator.
But again, the scholars of the time consistently included incorrect material alongside breakthroughs, as seen with the last line stating that division by 0 gives a fraction. The mathematical definition for division is the inverse of multiplication, such that A divided by B equals C. Thus, A must equal B times C. So, if we use this definition with 0, 5 divided by 0 equals 0, then 5 must equal 0 times 0, which it does not. This would violate the definition and be considered a false statement. So we must deem this undefined. Otherwise, there would be a fundamental contradiction and the breakdown of logic and thus the system. Math is a formal system of logical reasoning from a set of clearly defined axioms to allow for irrefutable truths, what we call theorems, within the system. Allow a contradiction, and the system falls apart, and you can prove anything. Thus, everything becomes meaningless, unable to discern truth from fiction. It might be possible to construct a system that allows for contradictions without rendering the system useless, but I don't know, and that's way beyond the scope of this video. We now move to the Middle East, where a new capital called Baghdad will be established. A now ancient city faced with hardship in the modern day, at that time was shortly to become the new epicenter for mathematics. This transformation followed the expansion of Islamic influence under the leadership of the Prophet Muhammad, who, after escaping an assassination attempt in 622, migrated to Medina and assumed both religious and political authority until his death in 632. His passing did not halt the momentum of Islamic conquests. Cities like Damascus, Jerusalem, Mesopotamia, and by 641, Alexandria, a former bastion of mathematical thought, were swiftly brought under Islamic control. Legend has it that the leader of the victorious troops, having been asked what was to be done with the books in the library, was told, "Burn them." For if they were in agreement with the Quran, they were superfluous. If they were in disagreement, they were worse than superfluous. Finally, by around the year 750, the war drums would stop beating. Baghdadians at that time were called scholars from Syria, Iran, and Mesopotamia, including Jews and Christians, making the city a sort of new Alexandria. The diversity of the empire was so heterogeneous, the Arabic leaders were, at first, without intellectual interest, and they had little culture to impose on the peoples they conquered. But eventually the Arabs would be ready to have history repeat itself, for the conquerors became eager to absorb the learning of the civilizations they had overrun. In this respect, we see a repetition of the situation when Rome conquered Greece, of which it was said that, in a cultural sense, captive Greek took captive the captor Rome. But unlike Rome, this society actually preserves merit rather than succumbing to purely abusive politics and exploitative military tactics.
The Arabic miracle is not reflected so much in the rapidity of the growth of their empire as in their intellectual tastes being aroused, digesting and absorbing the learnings of their neighbors.
Had it not been for the sudden cultural awakening in Islam during the second half of the 8th century, considerably more of ancient science and math undoubtedly would have been lost. It was during the caliphate of Al-Ma'mun that Arabs fully indulged their passion for translation. The caliph is said to have had a dream in which Aristotle appeared, and as a consequence, Al-Ma'mun determined to have Arabic versions made of all the Greek works he could lay his hands on, including Ptolemy's Almagest and Euclid's Elements. Muhammad ibn Musa al-Khwarizmi wrote 2 books, one of which survives only in a unique copy of a Latin translation with the title De Numero Indorum. In this work, he gives so full an account of the Hindu numerals that he is probably responsible for the widespread but false impression that our system of numeration is Arabic in origin. Subsequent Latin translations of his attribute not only the book, but also the numeration to the author. His most important book supplied us with an even more popular household term, the word algebra, becoming the father of algebra, and rightfully so. While he wrote the book entirely in words, including the numbers, it comes closer to the elementary algebra of today than the works of Diophantus or Brahmagupta, seeking solutions of equations, especially of second degree. Chapter 4 includes 3 illustrations, one of which is x squared plus 10x equals 39, in which case only the positive answer is given. No branch of mathematics springs up fully grown, and we cannot help but ask where the inspiration for Arabic algebra came from. The Arabs in general loved a good clear argument from premise to conclusion, as well as a systematic organization. The Hindus, on the other hand, were strong in association and analogy, in intuition and aesthetic imaginative flair. The Arabs just seemed more practical-minded and down-to-earth in their approach to mathematics. For it produced not only in the first half of the century, but also Tahbit ibn Qurra in the second half. He was the founder of a school of translators, especially from Greek and Syriac, and to him we owe an immense debt for translations of works by Euclid, Archimedes, Apollonius, Ptolemy, and Eutychius. He had so thoroughly mastered the content of the classics he translated that he was even able to suggest modifications and generalizations. It should be emphasized once more that within the confines of the Arabic Empire lived peoples of varied ethnic backgrounds: Syrian, Greek, Egyptian, Persian, Turkish, and many others. Many of them shared a common faith, Islam, although Christians and Jews were tolerated. There was considerable fractionism at all times, and it sometimes erupted into conflict. Tahbit himself lived in a pro-Greek community, which opposed him for his pro-Arabic sympathies. This is seen in mathematical works from the 11th century, where different works use Hindu numerals, while other times the Greek alphabet pattern of numeration was used. But in general, Arabic math can be divided into 4 parts. An arithmetic derived presumably from India and based on the principle of position. An algebra, although from Greek, Hindu, and Babylonian sources, nevertheless in Muslim hands, assumed a new and systematic form. A trigonometry, the substance of which came chiefly from Greece, but which Arabs applied new functions and formulas. Sometimes attempts are made to attribute the functions tangent, cotangent, secant, and cosecant to specific times and even to specific individuals, but this cannot be done with any assurance. And lastly, a geometry that came from Greece, but to which Arabs contributed generalizations here and there. We finish this era with one final mathematical genius, Omar Khayyam.
Whoever thinks algebra is a trick in obtaining unknowns has thought it in vain. No attention should be paid to the fact that algebra and geometry are different in appearance. Algebras are geometric facts which are proved.
He provided geometric solutions to cubic equations through the innovative use of conic sections, laying the groundwork for advances in algebra and geometry we still emphasize in teachings today. Omar would come close to a definition of a rational and struggled with the concept of real numbers in general. The origin of Pascal's triangle arrangement is often attributed to Khayyam, but no evidence is available substantiating that claim. The arrangement also popped up in China around the same time, so perhaps there was information trickling along the Silk Route connection between China with Persia, and we may never know who identified it first. When Omar died in 1123, Arabic science was in a state of decline. Excesses of political and religious factionalism, a condition that is well illustrated by the origin of our word assassin, would seem to be among the causes of the decline. Islam never again was to reach the scholarly level of this glorious age, but Muslims' contributions did not come to a sudden or abrupt stop. This video, however, is.